In this class we'll be discussing more general form of Clapeyron's three moment theorem, which can be useful for if there is any settlement or sinking of support, or even if there is a change in moment of inertia I of two consecutive span, or even if there is a change in the material property, that is Young's modulus. So this is the most general form of Clapeyron's three moment theorem, which tells MA, that is fixed end moment at most left end. So again, say there is a beam, continuous beam, and then this is say it is continuing, this is middle. Okay, so this is say B, this is A, this is C, this is left end, this is middle support, and this is right support. So if there is a this portion of this beam is having different material property, for example this is of steel, and then this span is of say concrete, no doubt practically it is difficult, but even though if in some situation you can have the beam with two different material, so in that case the Young's modulus of this span will be different, Young's modulus of this span will be different. Also the cross section area of this beam can be different. So say this cross section area of this span has some say 150 mm width, and this is 300, and here say it is 150 into say maybe 600 mm. So if cross section areas are different, then definitely moment of inertia of this two beam will change. So and then again, if say this or this or this, any one of this support, or maybe more than one support sinks down or settles down, then how we can incorporate these things in the Clapeyron's three moment theorem, that we'll discuss today. So to discuss this, we need more general form of Clapeyron's three moment theorem, and this is the the form of Clapeyron's three moment theorem. So MA is a bending moment at left support, here in this problem, bending moment at left support, for example here it is. Then L1 is the length of first span, or say left span. E1 is a material property or Young's modulus of the left span AB here. Then I is a moment of inertia of this AB beam, or AB span. Then 2 MB, MB is the moment at B point or mid support. Then L1, E1, I1 we already discussed. L2 is the length of second span. E2 is the Young's modulus of the second span. Then I is a moment of inertia of this second span, or say right hand span. So left hand span, right hand span, or span number 1, span number 2. And then this MA correspond to the bending moment at left support, MB correspond to the bending moment at mid support, and MC correspond to the bending moment at right support. Then there is a slight change even on the right hand side of this equation. So remaining terms as it is, we already discussed, minus in bracket 6a1 x1 bar divide by, we already saw that it is L1, but in addition to that you will get E1 I1, then plus 6a2 x2 bar by E2 I2 into L2, right? Plus this is additional term that will have, and what this term is, 6 delta AB by L1 plus 6 delta BC, sorry, delta CB by L2. So this is very important, here it is delta AB and delta CB. So what is this delta AB? Then delta AB means say level or settlement of B support, sorry, settlement of A support minus settlement of B support, or settlement of left support minus settlement of right mid support. And delta CB means delta C minus delta B, which means settlement of right support minus settlement of mid support. So this equation is standard, these meanings are standard, you should not change. We cannot make it delta BC, so it is delta CB, and delta CB means settlement of right support minus settlement of mid support, and delta AB means settlement of left support minus settlement of mid support. So this is like a standard. So like if there is a settlement, then we can use this term and then we can solve. But for most of the beam, generally we cast a beam with a single material, maybe concrete or steel. So majority of the time this E remain constant, or it is like the same throughout the span. So this equation can be little bit more simplified, and even sometime or majority of the time this moment of inertia, that is cross sectional area of the beams, are same, then I will be same. So this is like typically we call prismatic beam if the cross section of the beam remains as it is throughout the length. So if there is a continuous prismatic beam, then I will remain same. So like if you use these two cases, like say if beam is cast with the same material, then it will be like say E1 and E2 will be equal to E, and like a moment of inertia I1 it will be equal to I2, and that we can write down I. So then the equation will be modified like this, right? So MA bracket L1 by EI plus 2MB bracket L1 plus L2 by EI plus MC in bracket L2 by EI, and equal to minus 6A1 x1 bar E I L1 plus 6A2 L2 6A2 x bar 2 by EI L2 plus 6 delta AB by L1 plus delta CB by L2. Right, so you may like bring this EI to this, or you multiply EI to all the or both the side, so this equation can be written. So in some book you may get this equation in this form or in this form, or sometime even in this form also, right? So I mean it is like up to you how you want to remember it, but any form is like okay, because since like majority of the time you will see E is constant, I is also sometime it is constant, but even though if it is different, then like how to incorporate that we'll see in the numerical example. So this is more general form of Clapeyron's three moment theorem, right, which includes the settlement term, which includes change in material property of two consecutive span, and it also includes the effect of change in cross section, that is moment of inertia of two section. Right. Other terms has the same meaning what we have discussed in previous class. For example, A here it represent the area of free or like release bending moment diagram, and X represent the centroidal distance. If it is like a left bending moment diagram, then we calculate the centroidal distance from left end, and if we are like say bending moment area is right bending moment diagram, then we calculate this centroidal distance from right support. So other terms you already know, so they will be as it is. Only difference is like this one bracket and this EI, right? So we'll see numerical how we can incorporate or how we can use this modified or more generalized Clapeyron's three moment equation. So we'll be discussing like say third numerical. So what is given? Analyze the continuous beam shown in the figure if the support B and C sinks by 10 mm and 15 mm respectively, given E is equal to 2 into 10 raised to 6 kilonewton meter square and I is equal to 1 into 10 raised to minus 4 meter raised to 4. So beam like A is a fixed support, then B is like a B and C are like a roller support, and then on AB span the load is acting 20 kilonewton per meter square, and the I is like a 2I here, and for this span it is like I only. So wherever like E is constant, so same E we can use for both the span. So you already know that to solve this problem we have to plot first the simply supported bending or like a free bending moment diagram, so in which we consider like each span as a simple support, and then we plot bending moment diagram for the given load. So for this given load, again it's UDL, so you'll get typically a parabola, and for this point load you'll get a triangular load. So like here we you can see we have calculated the maximum bending moment. So for parabola it is WL square by 8. So W is the intensity of UDL, which is like a 20. So 20 here, then 6 is the span of the first span. So it is like 6 square by 8, and it comes out to be 90 kilonewton meter. Now for BC span, for this BC span, the bending moment diagram, maximum bending moment diagram, maximum value of this bending moment is WAB by L, which will be below this point load. So which is equal to WAB by L below this point load, right? So this value turns out to be like 80 multiplied by 3 into 1 by 4. So this comes out to be 60 kilonewton meter. Now another important thing, like we need to we should know the centroidal distance from the support of this bending moment diagram. So for this parabola it is quite easy, since it is symmetrical, then directly we can write down it should be like this span by 2. So total span is like 6 meter. So it will CG will lie at 3 meter from both the end. But for this triangular portion, how we have to calculate? See, like if we know that this apex is like this apex distance from left support is A, and from here it is B. Since like this apex will be below this point load, so this is 3 meter and this is 1 meter. So you assume this as a say A, this is B. Then the CG is calculated using this equation. From left support it will be 2A plus B by 3, and from right support it is A plus 2B by 3. So like here A is 1, B is like a 3. So this 5 by 3, how it is coming? Then say like A is 3 plus 2 multiplied by 1 by 3. So it will be 2 into 1 is like a 2, and plus 3, so it will be 5 by 3. On this side A is like say 3, so 2 multiplied by 3 plus 1 by 3, so 6 plus 1, 7 by 3. So that's how like you can calculate sorry, that's how you can calculate the centroidal distance of this kind of triangular bending moment diagram from both the support. So this is like how we can calculate free bending moment diagram and how to locate their CG. Now next we have to calculate even the area of this bending moment diagram. So like if you remember, we need to calculate area. So like length of each span we know, Young's modulus we know, I like it is given. So these terms are given. Definitely this MA, MB, MC are unknown. Other terms what we have to calculate is area X bar. So X bar I already told how we can calculate. We'll calculate now this area in Clapeyron's 3-moment equation. So for like in last class we already know that if there is a fixed support, then we have to assume like an imaginary span of 0 length. So this length is 0. So we have to assume or like we have to replace this fixed end to a continuous beam with 0 span. Then if you see, this is the beam that we have to analyze, which will be, or like this beam we have to convert in, I mean this fixed support we have to convert it into the 0 span. So there will be like a 3 span, one this say A0 to A, second is A to B, and third span will be B to C. So in this case we have to use this Clapeyron's 3-moment theorem for 2 times. First for say A0 to, or like say like here we will be assuming this, instead of fixed support we will be assuming the imaginary span of 0 length, right? So now we have to use this Clapeyron's 3-moment theorem for A0 to A and AB. For this span we'll be using first time, and then we'll be using for AB and BC, this 2 span. So we have to use here Clapeyron's 3-moment theorem for 2 time, right? So we'll write down this Clapeyron's 3 moment theorem for 2 times. Now for AB there is no bending moment, so like area of this bending moment diagram or free bending moment diagram on A0 A span will be 0. For like a BC portion, for BC portion it is like for AB portion it is this parabola, which is like the area of this parabola can be calculated using 2 by 3 into base into height. So like 2 by 3 multiplied by 6 is the base and height is 90, which we have already calculated. So so it comes out to be 360 kilonewton meter square. Now for span BC, it is triangle, so easily we can calculate the area, which is 1/2 base into height. So base is like 4 meter, the span is 4 meter, height is 60, that we have already calculated here, right? So that's how we can calculate. Now this is the 3 moment equation. MA L1 by EI plus 2MB plus L1 by E1 I1 plus L2 by E2 I2 plus MC in bracket L2 by E2 I2, and then on right hand side is equal to minus in this bracket 6A1 X1 bar by E1 I1 L1 plus 6A2 X2 bar by E2 I2 L2 plus 6 delta AB by L1 plus 6 delta BC by L1. So this is the Clapeyron's 3 moment equation that we'll be using for span AB. We'll be using this Clapeyron's 3 moment equation for span A0, A and AB. So we'll consider this 2 consecutive span, or like say this 2 consecutive span will be applying this Clapeyron's 3 moment theorem on this 2 span. Now when we use this 2 span, that time this will be like our leftmost support. This A becomes like middle support and B becomes left support. So this here you need to be careful while writing the things. So MA is the bending moment at the left support. So like left support is I don't know how I should put it. Maybe like okay. So MA is the bending moment at left support, like left support. Here it is A0. Since like A0 is a simple support, so there won't be any bending moment. A in simple support, so there won't be any bending moment. So we can substitute M0 equal to 0. Then MB, this is small b, which represent bending moment at middle support. So this is bending moment at mid support, but here for this problem or this 2 span, this A is a mid support, so I'm writing M capital A. So this small b and this is capital A. So definitely we need to calculate this bending moment at A support. So this is unknown. Similarly MC, this is small c. So bending moment at right support. Now right support is B support. This B support is there as a right support, since we are using for this 2 span, this 0 length span and then this span, right? So bending moment at right support, that means bending moment at B point, so it will be M capital B, and that moment is also unknown, so it is unknown. Now L1 is 0, we don't know, I mean we know that this is 0 length span beam, so length is 0. EI like of this portion we can assume like infinite, so it has like infinite flexural rigidity, hence it won't get deformed, right? Then L2 for this 2 span, L2 will be the span length between A B, which is 6 meter, then E1 E2 I2. Now for this span we have to write down E2 I2. So from here you can understand like I is 2I, so that's how we can substitute here. E is given, E multiplied by I into 2, so like E is like a 200 into 10 raised to 6. This value is given in kilonewton meter square, and then I is given 1 into 10 raised to minus 4 meter square. But since like we have for this second span it is 2I, so we are multiplying by 2. So if you just simplify it, then what we will get is 4 into 10 raised to 4 kilonewton meter square. So like these are the values. Now we'll substitute them into like this equation. Now area is 1. Now again area of this A1 represent area of free bending moment diagram on left span A0 A, which is 0. There is no bending moment on A0 A span. Then A2 area of free bending moment diagram on right span AB is equal to 360 kilonewton meter square, which we have already calculated. It is nothing but the area of the parabolic bending moment diagram. Then this is important, x1 bar. So this x1 bar is the distance of the bending moment diagram from the okay, so x1 is the centroidal distance of free bending moment diagram from the left end support of span AB. So this bending moment, since we are using for this, so this is like left span, and on this span whatever is the bending moment diagram, definitely it is 0, but by chance if we have something, then we should measure it from this end, and for this second span we have to measure it from this end. So this will be our x2 like for this two span, right? So that's how like centroidal distance x2 bar is equal to like a 3 meters, since it is symmetrical, that we already calculated. Now delta AB, delta of left end minus delta of mid end. So left end is A0 and mid end is A, and since both A0 or like A is not sinking, so or there is no settlement of A support, and definitely A0 is not settling, since it is like imaginary span, so we are not assuming any settlement in that support. So then this difference will be 0. Now delta BC, that is delta of right end minus delta of mid end. So right end is now B, right? So delta of B support, which is sinking by 10 mm, and delta A, which is not sinking, so this will be 10 minus 0 equal to 10 into 10 raised to minus 3 mm. Sorry, this will be in meter. So this is in mm, so like you can convert it into the meter, so multiplied by 10 raised to minus 3, so this will be 10 into 10 raised to minus 3 meter. So now we'll substitute all this value in this Clapeyron's 3 moment or generalized Clapeyron's 3 moment equation. So first portion, this MA, small ma is now MA 0, and this anyway 0, like you can discard this term anyway. Then 2 MB, that small b, but that small MB here it is like M capital A. So 2 into MA. Then this portion anyway it will be 0, there is no bending moment, so area is 0, so like it is 0 by infinity, you can say. Then plus for second span, it is like L by EI. So L is like 6 meter, this portion has like a length of 6 meter, and then divide by 2 EI. So like EI we already calculated, we are multiplying by 2 outside, or directly you can write down 4 into 10 raised to 4, right, which we have calculated previously. And then for like again MB, that is bending moment at right support, and here right support is this B support, right? So that's how it will be 6 by 2 into 2 EI again. So EI is 2 into 10 raised to 4, so multiplied by 2. Then right hand side of this equation, minus 6 multiplied by A is 0, this x is 0 divided by infinity plus 6 into area of second bending moment diagram. So here it is area of this parabolic diagram, right? So it is 360 multiplied by 3, that is centroidal distance, divided by 2ei multiplied by 6, that is L2. So this is nothing but E2 I2, this is like L2, right? So here anyway E1 I1 is infinity. So that's all. And then delta AB, anyway it is like a 0, so we are substituting delta AB 0. So like we are using this equation, right? So delta AB is 0, so here it is 0, and then delta CB, which is as such here delta B minus delta A, so that like we already calculated, and it is 10 into 10 raised to minus 3 meter. So 6 into 10 raised to 3 10 raised to minus 3 by like L2 by L2, so L2 is a 6 meter, so we are substituting it here. So then after that you just simplify this, and then easily you will get one equation, that is 6ma plus mb is equal to minus 113.33. so this is my second equation. Now will be so we have used this Clapeyron's 3 moment equation for first two span, that is A0A and AB span, right? So we have used this Clapeyron's 3 moment theorem for this two span. Now we'll be using for this two span, right? So now when we use this two span, that time this A becomes left support, B becomes mid support, and C become right support. So when we did for this one, that time this was like a left support, this is middle support, and this is right support, right? So we'll use the Clapeyron's 3 moment equation for AB and BC now. Okay, so applying 3 moment theorem equation for span AB and BC. So MA, now it is the bending moment at left support, and left support is now A, so it will be MA, which is unknown, we don't know. Then MB, that is bending moment at mid support, and now it is like MB only, but it is capital B, and that is also unknown. Then small MC, that is bending moment at right support, which is like simple support or end roller support. So here the moment will be 0, so that's how this is like simple support, so this is like a known, so we can substitute that value. Similarly, the length of first span, now this will be the first span, this will be the second span, or this is like left span, this is right span. So length of first span is 6 meter, then EI is equal to 2 EI, so 2 multiplied by 2 into 10 raised to 4 equal to 4 into 10 raised to 4 kilonewton meter square. Similarly, L2 is like a length of second span, the second span, which is 4 meter, and the flexural rigidity is I here, so it will be EI, which is equal to 2 into 10 raised to 4 kilonewton meter. Now A1 is the area of free bending moment diagram on left span AB. So left span AB, which is like this parabola, we already know the area is 360 kilonewton meter. Similarly, E2 is the area of the bending moment diagram of right span. So this right span, we have already calculated it, and it is 120 kilonewton meter square. And then centroidal distance. So here like you need to be understand one thing. Now centroidal distance of free bending moment diagram for the left span AB is 3 meter. Now in previously when we used this Clapeyron's 3 moment theorem for this two span, that time we calculated the centroidal distance of this parabola from this end, because that time this was like a right end, but now it becomes a left span, so we have to measure this from this end, not from this end, right? So we'll be using now here this 3 meter is this distance. In previous case 3 meter was this one, right? So it is 3 meter. Then x2 is the centroidal distance of free bending moment diagram of right free bending moment from right end of span BC. So this distance, now we have to measure it from right support right, which is like 5 by 3. So it is 5 by 3 meter. Now again delta AB is equal to delta A, that is like level or the settlement in A or left support minus settlement in mid support. Now left support is not sinking, that is A support is not sinking, but since B support is sinking by 10 mm, so it will be minus 10 mm. So that's how this you cannot do delta B minus delta A, it should be delta A minus delta B only, or like delta of left support minus delta of mid support, and here it is delta of right support minus delta of mid support. So you have to subtract the delta of mid support in both the cases. So in both the cases we have to subtract the delta of mid support only, right? That will give you this plus or minus sign, and with that plus or minus sign only we have to substitute the value in this final equation. So here we are getting minus 10 into 10 raised to minus 3, whereas here we are getting 5 into 10 raised to minus 3 meter. So we'll substitute all this value in Clapeyron's three moment equation, and like if you substitute those all values, like here I'll just read it, it is 6 by 2 E, since like for this left support it is EI, and for right support it is I, or say EI. So here it is like, this is like L1, this is I1, L1 I1, so which is 2 times EI. So like we are substituting that, then 2 multiplied by MB, 6 by 2 in bracket 2 into 10 raised to 4 plus 4 by 2 into 10 raised to 4. This is like a EI of this band, right? So that's how it is, we are not multiplying by 2. Then MC, so like L by EI, so like for second span it is only EI, so we are not multiplying by 2, equal to like say right hand side. So we'll substitute the values in right hand side part. So 6 multiplied by A1, which is 360, then multiplied by x1 bar, which is 3 meter, then 2 EI multiplied by L1 6 meter, plus 6 multiplied by 120, that is area. Then this is centroidal distance of right bending moment diagram from right support, which is 5 by 3 meter. EI is like 2 into 10 raised to 4 multiplied by L2, which is 4 meter, plus now we'll substitute deltas. So deltas, like these values we have to substitute, which is 6 delta AB. So 6 into delta AB is 10 raised to minus 3, so 10 raised to minus 3 by L1, which is 6 meter, and then plus 6 multiplied by delta CB, like delta CB is 5, positive 5, since like delta C, that support C is also sinking down, so it is sinking by 15 mm, and the mid support is sinking by 10 mm. So value what we are getting is like 5 into 10 raised to minus 3 meter. So 6 multiplied by 5 into 10 raised to minus 3 by L2, which is 4 meter. So like if you substitute these values and simplify all this calculation, so after simplifying this all calculation, what we are getting is this value. So like what I am doing, I am like making this uniform denominator on both the sides. So I'm multiplying by 4 into 10 raised to 4 on both the sides. So I'm getting this equation, and like if you simplify further, then this is like 3a plus 14 mb equal to minus 390. This is the equation we are getting, that is like equation number 3. Now equation 3 and equation number 2, this equation what like we have already got when we implemented this Clapeyron's three moment theorem first time, and this is the equation when we this equation we got when we apply this Clapeyron's equation for second time, right? So this is from A0A and EB, and this is from EB and BC, right? So this two equation we are getting by implementing Clapeyron's three moment for this two like cases. So when we solve, like we can easily solve this two simultaneous equations. So if you solve those two simultaneous equation, then easily you can calculate like MA, which is like minus 12.30 kilonewton meter, and MB comes out minus 39.50 kilonewton meter. So once we calculate that, we have to calculate the final reactions. So final reaction, to calculate this final reaction, what you can do, you can draw free body diagram of each span. So this is span AB. Now we already got the value of MA, which is 12.3. MB we already know it is like 39.5. Then we have to calculate this vertical reaction. Since we have done this already in previous some problems, so I'm not doing it in detail. Then like if you draw free body diagram of BC, then there will be a moment MB. Now both will be like a negative or like a hogging moment. So like when you draw BC, that time it will be anti-clockwise, but for BA it will be clockwise moment, right? So but both will have the same value of 39.5 kilonewton meter. And then this load. So like if you use condition of equilibrium for this part separately and for this part separately, easily we can calculate the vertical reactions. So like when you take a moment about A for AB, then like we can get the value of VB1, which is equal to 64.53 kilonewton upward. And then if you use second condition, that is like the summation of vertical force is 0, then we get V equal to 55.47 kilonewton upward. Similarly for span BC, when we draw free body diagram, then take a moment about say B point, and then like easily you can calculate VC, which is 50.125 kilonewton upward, and VB2 is like 29.875 kilonewton upward. So finally, like final vertical reaction at B support will be the addition of this VB1 and VB2, which is equal to 64.53 plus 29.875, and it comes out to be like a 94.41 kilonewton. So after that, like we have to plot shear force bending moment diagram. So like we have to plot shear force bending moment diagram. So before like doing that, I am just writing all the moments. Since like now we are plotting full beam, we won't be showing that MB moment. Now already that moment is internal moment, right? So what are the moment that get transferred from this span to this span and this span to this span, that we represent or that what we have calculated. So but then M at A, this is like a support moment, so we have to consider that. So vertical reactions we have, then support moment we have. So from that, simply like you do shear force calculation that we have already discussed many times, so I'm not writing those calculation, but this is what is the shear force diagram that we'll get. Again, we have to calculate the location of the point of contra shear, and there we can calculate the maximum bending moment. Now then plotting bending moment diagram. So bending moment diagram, again you can we already know these moments. Like we have to superimpose this mu and mu dash diagram, so that we already discussed, so I'm not going to discuss it in detail here, but then we can write down this. Otherwise we can write down like bending moment calculation, and then we can plot it, right? So again, bending moment mx equation I'm writing, and I'm calculating at mid span at 3 meter. Like it is 64.11. definitely you calculate this point of contrast shear location, and below that point of contrast shear, again you can calculate maximum bending moment. Actually that needs to be done, but anyway, I hope you can do that. That is not an issue for you. You already know how to do those calculation, and we have already discussed many times this shear force bending moment diagram, so I'm not going to discuss it, or I'm not showing here those calculation. Right, so this is the end of like a 4th unit, and in next class we'll be discussing some more. Some 2 topics are left from unit 3, that is influence line diagram and 2 hinge arches, that we'll discuss in next class. But before that, you'll get one assignment on this Clapeyron's 3 moment theorem. So I'll submit it on like our portal. Thank you.